is called root test. And the structure of root test statement of it is very similar. So it goes like this. You have a series, which is n goes from 1 to infinity, and then you have an. Okay, same setting. And then suppose this time I don't care about the the ratio of one term to the previous term. Instead, suppose limit n goes to infinity, nth root of the absolute value of the nth term is L. Converges, and converges to some number called L. And once again, L is not negative because see how here I impose the absolute value set, so everything is positive here. And so that limit L, according to this assumption, it exists, and that limit L can never be negative number, right? So it works 0. So then I have 3 scenarios. If L is strictly less than 1, right? Then summation n to 1 to infinity, original series, without imposing the absolute value, returns what? Very similar to that one. What am I going to say? Converges what? Absolutely. Absolutely. Number 2, if, however, L is greater than 1, then sorry, it's very bad. What happened? The original series diverges. Third one, if L is exactly equal to 1, then, sorry, it is what? It's inconclusive. Then this test, this ratio test, this test is useless, is inconclusive. When is this useful? You take the nth root. So there's a one kind of problem. For example, summation. Here's the example. Usually you have naturally some sort of nth power. Then you take the nth root, you get rid of that nth power. Okay. So let's see. So here's one example. What do you think? Well, an plus 1 over, absolute value again. Absolute value, not over, because I'm not using ratio tests. So an absolute value taken nth root. So what is that? So if I were to take limit n goes to infinity of this guy, that's the same as limit n goes to infinity what? Yeah, 2n plus 1 over 5n plus 3. Right? Because after imposing absolute value, you get this. Take the nth root of this nth power. What is that? It's just this base sum. Right? And what is that? 2 or 5. What do you say? Less than 1. Therefore, the series what? Converges absolutely. So is it possible for you to have a series which you happens to use just root tests and you prove that it conditionally converges? Is that possible? Let me say again. Is it possible for you to have you encounter a series, and then you use, root tests, and you say, aha, then this series converges conditional. Is it possible?
No.
No. Why? Because if you use root tests, there's only 3 possible scenarios. Is that right? Either, if you prove it, if it is happens the first scenario, then not only does the series converge, it converges what? Absolutely. If it is this scenario, then it diverges anyway. And so, and if this one, then you have nothing to say anyway, right? So under no circumstance would you use the root test to conclude that is what? Conditionally convergent. It's just impossible. All right? Okay. So, for example, once again, if you have, let's say, take that quiz example again. All right? Take that quiz example again. That is what? This one, and then 4 over n squared minus 1. N goes from 2 to infinity. And if you were to use root tests, then you would have to do 4 over n squared minus 1, take the nth root, right? And then see how it goes. And that itself is not an easy task. Right? Okay. Can I erase this? The statement, is that okay? Statement of the text. Right? So you would do this, and then it takes a little bit maneuvering in order to make it to work. So this is a n absolute value and take the nth root, right? And that's equal to that. What can you say about this? This is 4 over n squared minus 1 to the what? 1 over n's power. Is that right? So this is 4 to the 1 over n's power. That part is easy. That goes to what?
0.
This goes to 0, so 4 to the 0, that's 1, right? And then n squared minus 1 taken 1 n's root. How are you going to deal with it?
Freak out.
Seriously, how do you deal with it?
You separate.
Yeah, I'll do that. So perhaps I'll say, okay, I examine the tendency of this guy. All right? And this one is e to the what? ln n squared minus 1 and 1 over n's power, correct? And then I'll go e to the, pull out 1 over n, becomes ln n squared minus 1 divided by n. And then I have to ask myself separately, which I do over here, what happened to this exponent? Then I'll go limit x goes to infinity, x squared minus 1 over, ln x squared minus 1 over x. I said a long time ago, when x is very big, the x squared minus 1 is pretty much x squared. And you take logarithm is 2 times logarithm x. Is that right? Now logarithm x is growing, so is x. Which one grows faster? X. And therefore this one, if you use L'Hopital rule if you want, and I skip the step. But you have to understand, you have to have this intuition that a logarithm grows not as fast. It's actually very slow. And this is pretty much 2 times logarithm x. So 2 times logarithm x grows very slowly. So this numerator grows very slowly in comparison with the denominator. And therefore this is what? 0. So this one approaches what? 0. So this one approaches what? E to the 0, which is what? 1. And therefore you go back here. This approaches 1. This one approaches 1 as well. So 1 over 1, which is what? 1 inconclusive. Of course, right? So unfortunately. Right? So this is a lot of wide class of examples. You just can't do this. And you can see that this generalizes. If you have previously I say ratio tests, if you have a situation in which the an is actually a rational expression of n, right? Then this is useless. And more generally, if you say not rational expression, not polynomial or polynomial, but instead of polynomial or polynomial, say numerator is not a polynomial, but say square root of polynomial, same thing. For more or less the same reason. The ratio test is useless for that kind of cases. Likewise, if you have polynomial over polynomial, say you have x squared plus 1 over x fourth power plus x squared plus 1. And then you have n's power. Oh, sorry, not n's power. Just this is polynomial, right? And then if you attempt to use root test, then what happens? Then you'll have to take x squared plus 1, x fourth power plus x squared plus 1, and then take the nth root. Is that right? Then you'll have to do what? You have to say x, what did I say x? I mean n. Right, n squared, and I meant n, I didn't mean x. So this is an equal to n squared, n fourth power plus n squared plus 1. So n squared, n fourth plus n squared plus 1, take the nth root. And that would be n squared plus 1 to the what? 1 nth power divided by n fourth power plus n squared 1 and then raised to 1 nth power. Is that right? Then at first I don't know how to deal with this, nor I know how to deal with that. But then I remember that, so for the numerator itself, I'll take the logarithm and then exponentiate it, right? And so the numerator is a logarithm. Logarithm of what? Logarithm of this guy. And then pull this to the front, that means 1 over n times logarithm of something. Is that right? And then that thing, that exponent is 1 over n times logarithm of something. And then think of it as logarithm of something divided by n. And that one approaches what? 0. Right? Because logarithm grows very slowly. So then you write it down. So suppose you write, you investigate n squared plus 1 to the 1 over n's power. That is e to the logarithm of that. But logarithm of that is this. Right? Okay? So this is, if you look at numerator, it's logarithm of something over n. And logarithm grows very slowly. And therefore that quotient, goes to what? 0. And therefore this whole thing goes to e to the 0, and therefore 1. So this one goes to what? 1. Likewise, the denominator goes to 1. So you end up having what? 1 over 1, which is 1. So this is what happened if you have an equal to a rational expression, for which not only is ratio test useless, likewise, root test is useless. Okay. Get the idea? So, don't attempt to use ratio test. And you have to feel. How do you feel it? How do you feel it? Like n to the third power. How do you feel it? N to the third power. Let's say numerator is n to the third power. And then if you go from one term to the next, then this numerator grows. Agree? Granted. Right? For example, 100 to the third power. Next term, the numerator will what? 101 to the third power. Granted, it's growth. But growth marginally. Why is so? Because the next one will be n plus 1 over third power. And so this over this. I'm just focusing on numerator, for example. Denominator is the same thing, right? The numerator goes like this. Going from this one, it grows a little bit, and you try to see how fast it grows. Rather than that growing ratio. Is that right? So, well, that will be this. Is that right? Then the thing is that this one is fixed. And therefore, you go something like this. If you organize this way, this guy is fixed. This one, if this is 100 or 1, this is 100, practically 1 anyway. Is that right? So raise the fixed power, what do you get? 1. Well, you get 1. Is that right? So it's useless. Useless. You have to feel how fast it grows. Yes, but the neighboring term, doesn't. You know what I mean? So we begin to feel that, this ratio is practically 1. And therefore, forget it. It doesn't work that way. Unless you use a Gauss convergence test, and that'll be something else we don't talk about. All right? So, but for this is there, Gauss convergence test is actually very cool. So, if you're interested, just let me know. I'll point you in the right place.